don't know what time is it in your country, but it's 7:47 Montreal. I welcome you to this session on electromagnetic transients. My name is Jean Massarejan. I am the chair of this session. So we have several very interesting papers to present today. We will basically start with the first one. We have 15 minutes for each paper. If you have questions, you have to use the Q&A window. And then I will read the question and we'll ask the presenter to answer them. The first paper is Interpolation for Power Electronic Circuit Simulation, revisited with matrix exponential and dense outputs. The presenter is Zixiang Meng. Zixiang Meng received his bachelor degree in electrical engineering from Tianjin University in China in 2018. He is currently pursuing the master's degree in the School of Electrical Engineering and Automation at Tianjin University. His research interests include simulation of electromagnetic transients, power electronics, and MMC HVDC. Please, Mr. Meng, you can start presenting now.
Hi, everyone. It is my honor to introduce some of our recent research here. The title is Interpolation for Power Electronic Circuit Simulation Revisited with Matrix, Exponential, and Dense Outputs. The following content contains 5 sections. The first section is Introduction. Why did we start the research? There were 3 reasons. With large-scale application of power electronic equipment, the power system is facing unprecedented challenges in its operation and control. A recent study, this paper reported the accuracy degradation of EMT type programs in power electric simulation because the way of handling the switching events generally introduce a great error than the integration method. In our previous research, we proposed the matrix exponential based method, and it is a fairly accurate algorithm. Correspondingly, it is affected more by the way of handling the switching events, which leads to a greater degradation in accuracy. In the following PowerPoint, we use MEXP to refer to matrix exponential based method. So we would like to design a high precision matrix exponential based method solver suitable for power electronic simulation. In the second section, I will introduce the matrix exponential based method and high order interpolation based on dense output. Power electronic circuits always contain a large number of switches. The state space model of a system with P independent switch groups has a general form as I show here. It is a piecewise linear model, and the state matrix A is dependent on the switch status values Si. Si represents the state of the I independent switch group, which is our binary value. For a linear system, assuming a constant Ut over the interval T0 to T0 plus H, the simplest exponential integration formula is as follows. It turns out this formula is sufficiently accurate for a large portion of power system simulation studies, and it is especially attractive due to its high accuracy. And this is the matrix exponential term. Efficiently solving this term is the key to practical application of this formula. And currently the best way is the scaling and squaring method, which mainly uses Pardee function approximation, where K and M are the order of the numerator and the denominator of Pardee KM approximation. The local error introduced by the Pardee KM approximation is of K plus M plus 1 order. This equation illustrates that we can adjust the accuracy of matrix exponential operator by adjusting parameter K and M in Pardee approximation. If we want to use high order interpolation to adjust the interpolation accuracy, we need additional internal points. In our previous work, accurate dense output formula is proposed based on the scaling and squaring method. The formula can return additional internal outputs, and this formula returns the first S output located at these time points. This formula reuses the intermediate results of the scaling and squaring method, so it has no additional cost. And because these dense outputs amount to simulation results of rapidly halved step sizes, their accuracy is no worse than that of the original X. So dense output formulas are efficient methods to get internal outputs. Next, to improve the accuracy of the way of handling the switching events, the process of quadratic interpolation based on dense output formulas is proposed. What is special is that we use dense output formulas to get the inner output at TD. If we use the outer output at T0 minus H to do quadratic interpolation, there will be no accuracy improvement, so the inner output is necessary. In section 3, we propose a matching strategy and design solvers based on this strategy. Firstly, we list the error sources of matrix exponential-based method, EMTP, and Piscard. The common point of the three methods is that they all have higher accuracy in simulation without switch events, and will face the problem of precision reduction when switch events occur. What are listed above are local error sources, but how about the global error? The effect of local error accumulation on global error is summarized in this paper. Assuming the dominant local error is Q order, difference on steps of dominant local error lead to different global error. If the local error at all steps are dominant errors, the global error is Q minus 1 order. If the local errors at switch events are dominant errors, the global error is Q order. According to error sources in table 1, EMTP, Piscard, and matrix exponential based method all belong to the situation B. So the accuracy of EMTP and Piscard reduced from second order to first order, and matrix exponential based method retains second order global accuracy in power electronic circuit simulation. So unreasonable combination leads to loss of integration accuracy. The matching strategy is proposed to avoid the accuracy loss. Assuming the errors are introduced only by numerical integration method and interpolation method, which are Q order and P order. When P equals Q minus 1, the global error determined by both methods is Q minus 1 order, so the combination is economical. When P equals Q, the Q order interpolation method is slightly more accurate, so it can hold the accuracy of the integration method to achieve better results. It makes sense when the added cost is only marginal. In short, the matching strategy is to combine Q order numerical integration methods with Q order or Q minus 1 order interpolation method. Based on the analysis, we can start to design new solvers. As we mentioned before, we can use Pardee approximation to adjust the accuracy of matrix exponential based method to match the interpolation method. Table 2 lists the potential options for matrix exponential approximation from second order to fourth order. Among them, the first row has the same form as the forward Euler method, which is not as stable, and the third row has the same form as the implicit trapezoid method and may face the problem of numerical oscillation. So the final reasonable choices are to combine Pardee 0,1 exponential formula with linear interpolation, and to combine Pardee 1,2 exponential formula with quadratic interpolation. For easy reference, these two options are abbreviated as EXP01L and EXP12Q respectively. In the next section, we present two case studies to demonstrate the proposed solvers and compare with EMT simulation tools. The first case is single-phase TCR circuit. In this case, the proposed solvers are compared with widely used EMT simulation tools, including EMTP, PISCAD, and Artemis. Because PISCAD cannot solve the ideal switches, the binary on-off resistance model of power electronics devices are adopted.
The column vectors of the
as figure 3 shows, the overall shape of simulation waveforms from different methods are close. Figure 4 shows the absolute errors between these methods and the analytic solution. The maximum errors of the first order accuracy method, EMTP, PISCAD, Artemis, and EXP01 use the EXP01L are in the range of 10. Although EXP01L uses the lowest precision numerical integration method, and the Artemis use the highest accuracy integration method. Their global accuracy orders are the same. MEXP proposed in previous research is also added to the comparison, referred as MEXPL and MEXPQ, which stand for the matrix exponential-based method combined with linear and quadratic interpolation, respectively. MEXPL has 3 orders of magnitude smaller maximum error compared with the first order method. MEXPQ and EXP12Q has additional 3 orders of magnitude smaller maximum error than MEXPL.
We could test the system in several phases.
Figure 5 shows the step size versus global error to show clearly the order of each compared solvers. EXP01 has the same order global accuracy with EMTP, PISCAD, and Artemis. EXP12Q has 3rd order global error, which is the highest among all mentioned methods. The curves of EXP12Q and MEXPQ almost coincide, which indicates that although EXP12Q uses a lower order matrix exponential approximation than that of MEXPQ, the accuracy reduction is limited.
So, a very interesting case of our approach. Because reminding that we will divide.
We lost you there.
One group associated.
Sorry, my PowerPoint. The second test case is an open loop nearest level controlled one-phase of MMC system containing 8 MMC submodules. The ideal switching model is used in this case. The step size is 20 microseconds. In this case, all compared methods still can get the right results. And the EMTP and the EXP01 has the largest error. EXP12Q and MEXPQ still have the highest accuracy. I'm sorry, there are some errors. Figure 9 shows the global errors of this method. From this case with ideal switching model, we can reach the same conclusion as the case with binary on-off resistance model. The simulation results show that the EXP12Q solver has good performance and applicability in high-frequency complex power electronic systems. After the bioanalysis and the case studies, we can draw the following conclusions. The way of handling the switching events generally limits the accuracy of the algorithms, and the combination of numerical integration method and interpolation method is important for the accuracy of the algorithms. A matching strategy is proposed to guide the combination of numerical integration method and interpolation method. Higher order interpolation methods which have good applicability to the matrix exponential based method are proposed based on dense output formulas. And finally, two new solvers are proposed for matrix exponential based method, which are stable, and one of them is more accurate than existing MT simulation tools in power electronic simulation. Thanks for your listening. That's all. Okay. 现在没关掉吗？没共享。Oh.
So they don't seem to have questions for the moment. Okay, a quick question. According to what I understand, are you suppressing numerical oscillations actually? Hello, is Meng still there? Did you hear my question? Did you hear my question? I was asking if you are actually suppressing numerical oscillations.
Hi, John. Maybe I can answer the question.
Yes, go ahead.
Okay, so the numerical integration method we use, which is the matrix exponential based method, it is the L-stable integration method. It's similar to the implicit Euler method. There is naturally there is no numerical oscillation phenomenon associated with the method. So in our case, we don't have the problem of the oscillation.
Okay, so we noticed also that for methods that do not have this possibility, the location of the discontinuity had impact on the accuracy. So it was not obvious to say that if you use interpolation, you have more error or less error. I don't know if you observe similar things in techniques that you do not necessarily use interpolation or do not use interpolation. The interpolation location had impact on the accuracy of results. Have you noticed something similar in your observations?
Yes. Actually, there is. We didn't compare these results in this paper, but I've observed in a previous paper which we showed in the slide that reported the accuracy comparison. They have several cases that they compare PSCAD and EMTP. We know EMTP don't have interpolation and PSCAD have interpolation, but according to their results, it is not always the case that PSCAD is more accurate or EMTP is more accurate. There actually, I think more detailed study can be done to show if it indeed is the case that interpolation always outperforms the method without interpolation. I think it requires more study.
Okay, I don't see any questions in the Q&A as far as I'm concerned. So first presentation, now we can go to the second presentation.